Alright, so in the previous video we started discussing the idea of waveguides, and the way the problem is set up is we had in the x direction a bottom plate and a top plate. The bottom plate was sitting at x equals 0 and the top plate sitting at x equal a. We set this up so that the wave propagated in the z direction, and we defined the propagation constant as gamma. We defined it with a bar over it, which will become a little bit clear later, because in the waveguide you'll find that things like the wavelength, the propagation constant, the phase velocity change because of the characteristics of the waveguide. So in addition to the property of the material, which would be just strictly a gamma, you also pick up properties of the guide. So we're just going to leave this for now until we have the solutions. We'll just leave this as gamma bar so that you know that it is different, since this is a waveguide. And the other thing that we said was we're going to let this waveguide be infinitely wide. So because of that, we have constant distributions of the fields in the y direction. So you don't have any variation of any of the components of either E or H in the y direction. So when we apply both of these, we find that Maxwell's equations, which were given in general form here for the curl of H and the curl of E, when we plug in 0 for derivatives with respect to y and we bring down the minus gamma for derivatives with respect to z, we find that those equations reduce to these. And when we do a similar thing in the wave equations, we find that the wave equations for E and H respectively are given by these two equations. Now notice that we have a common term E and a common term H here, that if we factor that out, we would get gamma squared minus j beta squared. So we're just going to give that the name of a single constant h to simplify the way the differential equations look. So doing that, then Maxwell's equations reduce to the following when we replace the gamma squared and the j beta squared, and we generate the h's here, and the wave equation does the same. So in general, all of the field components may need to be non-zero in order to satisfy the boundary conditions when we have a conductor or a dielectric. And that means both Z and H components of the electric and magnetic field. But it's basically, the way it's done is you divide this into special cases. So the first case that we'll look at will be transverse electric waves. In a transverse electric wave, the electric field components lie in the xz plane, so you have no z component of the electric field. And in the transverse magnetic field, you have no z component of the magnetic field. In a TEM wave, or transverse electromagnetic, both the z components of both E and H are equal to 0. So uniform plane waves are TEM waves, but not all TEM waves are uniform plane waves. So let's start with the case of the transverse electric wave, and in this case the y component of the z component of the electric field is 0. So the electric field is perpendicular to the propagation direction z, so it's 0 in the z direction, or no component in the z direction. So there is a value of the electric field in the z direction, but the component of the electric field in the z direction is 0, so it's not pointing in that direction. So for various reasons, we're going to solve for EY, because remember, the wave equation is actually 3 wave equations, one for each component direction. So since there's no z component, that goes away. So we would be left with an x component and a y component. So we're going to work with the y component first, remembering that that will be a function of x and z because E is constant in the y direction, the variation of field. So let's take the y component of E and plug it into the differential equation, which we simplified to include this parameter h. And also we know that we've said that all fields will vary as e to the minus gamma z. So this x and z direction variation can be simplified into a function of x and then e to the minus gamma z. And since this term is going to be common to everything, because we're only taking x derivatives, we'll just pull it out for now and we'll put it back in later. So now what we have is the second derivative of the y component of e with respect to x in the x variation plus h squared times e. And that's going to have a general solution of the sine and cosine. So we have c1 sine of hx and c2 cosine of hx. So let's go back and look right here is where our equation came from. So what we have to do now is we have this equation. It has undetermined constants, and it also has this parameter h. So now what we need to do is we need to find the boundary conditions. So first of all, we have to realize the electric field has to go to 0 at the top and bottom plates. So at x equals 0, all components of the electric field that are have to be 0. So EY is 0 at x equals 0, and it's also 0 at x equal a. So if we look at our equation here, and notice that I plugged the z dependence back in. If we look at our equation here, this cosine term, C2 is going to have to be 0 in order to satisfy this top boundary condition. So that then leaves us with the following equation. Now, if we look at what this boundary condition says, it says that this has to be 0 when x is equal to a. Now, that means that we've set a condition on h. So at x equal a, if we were to plug a in, the sine function itself is going to have to go to 0. So that would mean that h has to be m pi over a, where m is an integer 1, 2, 3, and so on. Now, what about h is equal to 0? Well, if we plug in h is equal to 0, that certainly satisfies the boundary condition. But if we plug in h is equal to 0, then the electric field is 0 everywhere, which means we have 0 electric field, 0 magnetic field, 0 everything. So an electric field cannot exist with m equal to 0. So we've got to have 1, 2, and 3 for our electric field in order to both have a field as well as satisfy the boundary conditions. So basically what happens is you have a different field distribution inside that waveguide excuse me, for different values of m. So for m is equal to 1, basically that electric field looks like a half sinusoid from bottom plate to top plate. So this would be looking to the down the end of the waveguide. So we have the top plate at A, we have the bottom plate at 0. This direction is in the direction of the width of the waveguide, so we're actually looking into the end of the waveguide. And what we see here is that E basically has, this is EY, so E has a Y component. That Y component varies. It's 0 at the top plate, 0 at the bottom plate, and it has this sinusoidal variation. And this is for mode 1. If we were to look at mode 2, we would see a different distribution, which would have a top lobe and a bottom lobe. If we were to look at mode 3, we'd have up, down, up, both ending at 0. So we basically have half cycles of a sinusoid between the top and bottom plate in space. And so this is at z equals 0. Now, if we now turn and look sideways at the waveguides, so now the horizontal axis is actually the z direction, or the direction of propagation. What we would see in the electric field is the electric field lines would be pointing toward us. And so these magnetic field lines, to obey the curl equation, are wrapping around the electric field lines. And if we look along the z direction, then as z gets greater than 0, because we've got variation in z of e to the minus gamma z, and gamma is j beta in this case of propagation, then basically we would have peaks, we would have sinusoidal variation along the z direction as well. So you have this pattern, and as you move in z, this pattern oscillates because it's also modulated by the fact that it's traveling in the z direction. So if you were to freeze in time and look at the distribution in the z direction, you would have sinusoidal variation of this amplitude as well. So it's a spatial pattern that varies from the top to bottom plate, looking at the cross section of the waveguide, as well as from end to end of the waveguide. The mode 2, and it's a little easier to look at the H field. Mode 2, instead of a single lobe distribution of the H field, it now splits in the top half and the bottom half. So your intensity would look like this, going from top plate to bottom plate, and then once again in the Z direction, that pattern is going to oscillate sinusoidally. Now we can do exactly the same thing for TM waves, and let me just go back a couple of pages before we leave transverse electric waves. Let's go back to these equations. Ones I want to look at are actually here. Because we have solved for EY and we have all of these coupled equations, we can basically apply Maxwell's equations in order to get a solution for the other components of E and for the other component and for the components of H. So they're related through Maxwell's equations. All right, so now the other kind of wave that we can look at is the transverse magnetic. And we would basically go through and solve for HY in exactly the same fashion that we solved for EY, applying boundary conditions in exactly the same way. The only interesting thing is we end up, because of the way the boundary conditions get applied and because of the constants, we end up with a cosine function for H instead of a sine function. And so what happens there is we can actually have an M equals 0. That won't result in a 0 H field or a 0 E field. It'll just result in a constant E field and H field. So the interesting thing then is if M is equal to 0, we basically have E perpendicular to H perpendicular to Z, and we have a propagating plane wave, because notice at M equals 0, your E sub Z goes to 0. So in that case, both the electric and magnetic field are perpendicular to Z, and they're perpendicular to each other, so we have a TEM wave. So the lowest order mode of the transverse magnetic wave, which is M equals 0, basically devolves to a TEM wave. So the TM0 and the TEM are the same in a parallel plate waveguide, and these are what the fields look like for the TEM wave. So you have a Y component of H, you have an X component of E, you have a Z component of E. And so this is an illustration, a picture illustration of the TEM wave. Once again, this is looking down the end of the waveguide. You see the distribution of the H field. This is for TM1. You see the distribution of the electric field if you look into the side of the waveguide. So this being the Z direction, propagation occurring in this direction. And here would be the second order mode of the TM, looking once again at the E field through the side of the waveguide. And the parallel plate TEM basically would look like this, where if you look in a cross section, or if you look, yes, there are cross sections, so this is looking down the end of the waveguide, you see this E field distribution and H field distribution. They're perpendicular to each other, and notice they are evenly distributed, so they're constant perpendicular to each other. And then if you look along the length, you can see here is this EX, because now we're looking, this is Z, so now we see these electric field lines. H would be pointed at you in this case, or let's see, it would be pointed, maybe be pointed at you in the plane of the perpendicular to the screen. So if you look here, you see basically this E field along the Z direction. If you freeze this in time, it's got a sinusoidal variation as well. So TE, TM, and TEM all exist in this rectangular waveguide.